Hey, today we have our lesson for related rates, and we are going to focus on the circles and the spheres. So those round shapes that are either two-dimensional or three-dimensional. In your notes packet, I am on page 29. So I'm still in that last section 311, but we're just doing the circle examples. So example 3, a balloon in the shape of a sphere is being inflated so that the volume is increasing by 50 cubic centimeters per second. At what rate is the radius increasing when the radius is 4 centimeters? So just like with the rectangles, just like with the triangles, we're going to start out with a picture. So draw yourself a circle. This is a balloon in a sphere, so if you want to try to make it three-dimensional, maybe something like that. And then we need to talk about what we know and what we need to find. So we know what was given in the problem is this 50 cubic centimeters per second. And we need to find the rate at which the radius is increasing when the radius is 4 centimeters. So that's a d something dt when the radius is 4 centimeters. So I didn't talk about variables yet. I kind of skipped over that part. We're discussing the volume of the sphere. So we need a volume equation. Volume is 4/3 pi r cubed. That's the volume equation for any sphere. So when I look in here, my variables are the volume and the radius. So those should relate back to the rates that you know. So we know dv dt, the change in the volume with respect to time. We want to find dr dt, the rate of change of the radius with respect to time. So what we need to do is look at our volume equation and find the derivative. So our derivative is going to be dv dt is equal to 4/3 pi. All of that is just a coefficient in the front. It just stays in the front. It's not 0. Some of you are going to be tempted to make that 0, but it's not. It just sits there. 4/3 times pi over 3 is going to be, a decimal a little bit larger than 4. And then the derivative of r cubed is 3r squared. And follow up with dr dt. And then these are nice. There's nothing you have to rearrange. You don't have to guess about what to put in. Just put in the values that you already have. We have, let's use some colors over here. dv dt is 50. That goes in over here on the left. And my radius is 4. That will go in over here. And then we're solving for dr dt. So let's scroll up a little bit. 50 cubic centimeters per second equals 4/3 pi times 3. The radius that was given was 4 cubed, 4 squared, dr dt. And then we'll divide all of this to the left-hand side. So 50 divided by 4/3 pi 3 4 squared is equal to dr dt. And you'll put all of that in your calculator. And as I'm looking at this problem, it just occurred to me there's a little bit of simplifying we can do. Here's a 3 in the numerator and a 3 in the denominator. Those are going to cancel out. So they don't even exist down here. Let me erase those. This 3 is gone, and this 3 is gone. Four pi, 4 squared. There we go. So in your calculator, you can convert this to a decimal. Just be very, very careful to use parentheses around the denominator. Otherwise, order of operations will fail in your calculator. So you want to make sure you put them all in. I'll show you how I do it. I have 50 divided by left parenthesis 4 pi times 4 squared. I'll show you. I don't know if you can see that. So there's my extra parentheses around the denominator. And when I hit enter, I have 0.248. So 0.24, I guess that rounds up to a 9. And I believe we're in centimeters per minute. Centimeters per second, excuse me. Centimeters per second. So that's the rate of change of the radius as we are inflating this balloon with air. Great job. All right, let's see if we can find a few more circle problems. Conical tank, we're not going to do those this year. You will be okay. Then we're on to the worksheet. We did the bus yesterday. We did the boat yesterday. The gravel problem, we're not going to do it all. Again, that's a cone. The airplane we did yesterday. Number 5, here's a balloon. This is almost like the problem we just did. That would be good practice. See if I can zoom in a little bit. The balloon in the shape of a sphere is being inflated. So here's my circle. So the volume is increasing at a given rate. So we know dV dt, and I'll look up above and see what that is in a second. We need to find dr dt when the radius is equal to 9. So when I look up here at the problem, dV dt 100 cubic centimeters per second. Now, it says it's being inflated. If it were being deflated, that would be a negative 100 centimeters cubed per second. But it's being inflated, so that's positive. So how do we relate the radius and the volume? That's easy. That's the volume equation. So volume is 4/3 pi r cubed. Find the derivative of this with respect to time. So dV dt is equal to 4/3 pi 3r squared dr dt. That's kind of like that implicit differentiation at the beginning of this unit. That's why they're grouped together. Look at those 3's. I see a 3 in the numerator and a 3 in the denominator. Those cancel out. And then we substitute the values that we know. We know that we are increasing at 100 cubic centimeters per second. There's my 4, there's my pi. The radius is 9 squared dr dt. To solve for dr dt, divide by all of that stuff. And then again, use your calculator, figure out what that decimal equivalent is. So 100 divided by, let's clear that out. Use your parentheses, 4 pi times 9 squared. Looks something like this. The light's not very good. Hit enter. So I have 0.098. And I'm a little out of space, but this is centimeters per second, linear centimeters per second. Great job. Now, I know Delta Math is kind of new. We're trying it out. I actually like it better than your textbook. I think the problems are more straightforward, and those help videos I think are very nice. Now, I did find out today sometimes the help videos don't always work on whatever device you're on. So if you're on your laptop, try your iPad. If you're on your iPad, try your phone. Try something to get those to work. I'm still learning the ins and outs of Delta Math, but I do think it's a good thing. Number 6 on this worksheet, number 7, we're not going to do. That's a water tank. That's a cone problem. But a circle, we should probably talk about a 2-dimensional circle. I kind of think that there's one on Delta Math. So let's just make up a problem. We have a circle. Let's say that the radius is, can't type today, is 6 and increases at 0.5 centimeters per second. What's the rate of change? What is the rate of change of the area? Change of area. All right. Hold that thought. I'll be right back. I have to pause real quick. All right, we're back. So what is the rate of change of the area? So if we have a circle, here's our radius. Area is pi r squared. That's the area formula for a circle. And then we take the derivative with respect to time. I didn't write your no and your find. I kind of like that. So we know that dr dt is 0.5 centimeters per second. And we want to find dA dt. When are we taking a picture with our phone? When is that exact moment? That exact moment happens when the radius is equal to 6. Okay, back to our geometric equation. Area equals pi r squared. So this is where we find the derivative with respect to time. So dA dt is equal to pi 2r dr dt. And if we fill in the pieces that we know, here's my pi, here's my 2, the radius is 6, the rate of change of the radius is 0.5, and all of this will be my dA dt. So 0.6 times 5 is 3, 3 times 2 is 6. So the rate of change of the area with respect to time is 6 pi inches squared per second. I guess centimeters, not inches. Okay, my units confused here. Centimeters squared per second. There we go. Now, in my calculator, I could take the decimal equivalent. I know some of you are not comfortable leaving that pi in there and you much rather have the decimal equivalent. That's fine. So 6 pi, I've got 18.8. dA dt is 18.85 centimeters squared per second. So again, I think there's some problems that look like that in Delta Math. I wanted to make sure you saw one of those. I know that they have helpful videos in there as well. It's not me teaching, but helpful videos in there as well. So hopefully that can help you out. So good job. Keep it up. I haven't heard from some of you at all. Please let me know how you're doing. Please turn some work in. You know that quarter 4 is pass fail, excuse me, but I'd love to see a little bit of something out there for you, especially before you head off to your next calculus class. So email me if you get stuck. If there are technology issues, let me know what's going on.